Rendering computer graphics is awesome. I mean, look at me. I'm in Night City with my main man V over there. What's up, V? But how is this possible? How did I get here? Am I bugging? Well, let's explore.
Hi.
Okay, so I found this reference image which I wanted to recreate. I got it into Blender and set up my camera on the floor. I also added a car, I got a human model, textured him, rigged him, and also got a jacket model which I also rigged to match the human. And then next up I outlined buildings in the scene and made simple shapes to fit the shapes of the buildings I'd outlined, and then for the texturing I just projected the reference image texture onto the buildings, and that's the Blender project all set up.
So I used this PBRT plugin for Blender, put it into Blender and hit render, and whoa, pretty, but there's no textures on it. So I'll fix that. I'll jump into the graph here, the material graph. We'll add some PBRT shaders and output some textures.
So let's make the rasterizer. One way a computer can draw graphics is via a process called rasterization, which converts a 3D scene into a 2D image viewed from position and rotation in the scene. So first I used the model class already set up for us to be able to load in models, and the TGA image class to write out to an output image. Now I just need to do something with the model and render it to the image that we're outputting. So we'll start off by being able to draw the wireframe of a mesh, and then I'll adapt the code to be able to render the faces of the model. This is done by taking 3 vertices that we're going to render and generating a bounding box around them. Now we can loop through each pixel and check if it's inside the triangle. This is done by using barycentric coordinates, which allow you to define a point in terms of 3 other points, u, v and w. If u, v and w are all greater than 0, then we know that the pixel's inside the triangle and can be drawn. And it's not much extra work now to render the texture onto this face. All we need is a texture and to know what point this pixel on the model's face represents in that texture. To do this, each vertex will not only be compromised of a position, but also a 2D texture coordinate between 0 and 1. We can use barycentric interpolation to work out the texture coordinate for that pixel, so we know how much each vertex texture coordinate will influence our texture coordinate for that pixel. So now we'll just sample our texture using that texture coordinate and draw it to the screen. To do backface culling, I read the normal of each vertex. We can then interpolate 3 of those normals to get a face normal. If the face normal is pointing in the same direction as the pixel to camera vector, then we'll render it, otherwise we'll discard it. The final big step we'll do is doing perspective projection and being able to move our camera around the scene. To understand this projection, you have to first understand that there's no absolute position, only positions that are relative to something else. And by default, your model will be relative to its origin, which is decided by the author of the model in their modeling software. Now normally this is at the centre of the mesh, but this means that each mesh may have a different origin point. And for us to be able to render them together, we need to transform them so they are both relative to the same origin point. Each object we want to render will have its own local to world matrix, which defines a transformation which can be applied to the model to put them into world space. By default, this local to world matrix is an identity matrix and so does nothing. But when we move the model around in world space, our local to world matrix will change. As we want to be able to position our camera in the scene, the camera will have its own local to world matrix. The camera starts at 0, 0, 0 and can be transformed and moved around the scene. But we don't render it from that world position of the camera. It's much easier to render the scene if the camera stays at 0, 0, 0, looking down the z-axis. So we can put the camera at 0, 0, 0 and transform every renderable object by the inverse of the camera's local to world matrix. A simple way of imagining this is that moving a camera forwards is the same as moving everything else the equal amount in the opposite direction. Now that we have our scene in camera space, we can convert it to projection space. This is another matrix transformation defined by this matrix. This maps all of the vertices on the screen to a -1 to 1 range called normalized device coordinates. Now we can apply our perspective to make faraway objects appear small and close-up objects appear large. And finally I'll create a z-buffer the same size as the pixel count for our image, And then when we go to draw a pixel, we can check this Z buffer. If the Z position of our pixel is less than what's already in the depth buffer, then we can draw it. If it isn't, we'll not draw it and just discard the pixel. This allows us to only draw the closest faces and remove hidden ones. And now we can render things like this. So finally, we'll make and render our scene using a ray tracer. Now ray tracers are much simpler than I thought they'd be. First of all, everything's in world space, which is nice. And a ray tracer works by tracing rays from the camera forwards. One ray will be fired for each pixel. Now in real life, the rays are shot out of the light source, which bounce around the scene and then enter our camera. We don't do this in ray tracing because the vast majority of these rays that leave the light source don't actually hit your camera, so we don't need to bother calculating them. And as the angle of reflection is equal to the angle of incidence, when we shoot rays out the camera, we end up with the same result anyway, and we don't need to waste time calculating all these rays that the camera doesn't see. Now we can use maths to tell if we're intersecting shapes. Spheres are really easy to calculate, but we can also find if we're intersecting with a triangle. And if we loop over each model and each of their triangles, we can tell if our ray intersects with a model. But this is very wasteful. Instead, we could have a box around each mesh, and when we trace our ray, first check if the ray intersects with any of the boxes. If it doesn't, we know not to check any of that model's triangles, which speeds up things a lot. Now a further optimization that can be made is using BDHs, which is the idea of bounding boxes that I just talked about but on steroids. The mesh is covered by a bounding box, and if the ray hits that box, then we have more boxes inside of that cover different parts of the mesh that we can test. In this example, you can see the ray hits the bounding box but misses the mesh, so we don't need to bother calculating the triangles. The amount of layers of these bounding boxes is configurable on a per model basis. In this example, the ray hits the first box and then hits a smaller box and then hits our mesh. So to make our ray tracer, I'll first clone this Git repo, which gives me the starting code for the ray tracer. It's able to read in models, output images and trace rays through the scene. It has a perspective camera and can render textures with a land ocean shader as well. It also has a directional and spotlight. I'll add in some objects into the scene, position the camera, and here is the image generated by the ray tracer and some other little cool stuff.
Oh, that's hot. That's hot.
Oh, I'm back again with a cap on this time. Wasn't that just a journey? Didn't we all have fun? Thank you so much for watching. Bye.